Thank you, Matthew. Thank you, everyone who joined. First, I want to thank my collaborators, Sankey Lee, Dongmin Kim, Robert West, and Ben Kirkman, which helped me put together this work. So as Matthew mentioned, today I'll be talking about the role of the ocean, specifically the Atlantic Whirlpool, in modulating extreme weather events. The overall goal of this project, which is basically a funded project by NOAA modeling, analysis, prediction, projection work, is to improve our understanding of high impact extreme heat waves in the US. And our main objective of this project is to understand the dominant factors modulating heat waves, also to look at relative roles of internal climate variability versus anthropogenic forcing when it comes to the occurrence of heat waves. And also, we want to identify naturally occurring potential predictors of these extreme events in order to improve not only their prediction, but also to look at beyond and their future projections. So what is a heat wave? Heat waves are large-scale, highly persistent extreme weather events that typically affect the mid-latitudes. They are basically the only extreme weather events that are large-scale in nature and persist for many days, even in weeks. And as you can see, they can impact large population areas. And typically, they occur on synoptic timescale, your weather timescale, 7 to 10 days, but they sometimes can prolong for much longer. And often they are associated with stagnant conditions weather-wise, as well as dry soil and dry conditions. And here I'm showing you how extreme these events are. For example, this is a vertical profile of temperature in red and moisture, a moisture variable, dew point variable in blue during heat waves that occurred in 2012 in the Great Plains. You can see that near the surface, these two variables are very far apart, with temperature reaching 45 degrees Celsius and dew points only about 4 degrees Celsius, which tells you this is a very dry condition during these heat waves. Also, the temperature profile, if you follow up, going from the surface upward, is very parallel to these lines, the red lines, which are the potential temperature lines, which tells you a very strong, persistent heating, near surface heating, as well as very persistent subsidence or sinking motion, which tends to prolong these events for many days. As you can see here by the vertical profile of the circulation, this is wind barbs as a function of height, very stagnant weather. So why we care about heat waves, and this is a motivation that I always talk about when I present this type of work, is that heat waves are responsible for the most weather-related cause of death in the US. And not only that, but their ratio of heat waves versus cold waves keeps increasing. So heat waves are becoming more common in present climate and as projected in the future climate projections. And these are some examples of deadly heat waves. And this year we have a very special case in the Northwestern Pacific section of our country, as well as in Canada, which was attributed over 1,200 deaths. And these heat waves that are occurring in the Pacific Northwest is also responsible for breaking the all-time temperature record for Canada. But it also affected states such as Washington, Oregon, and Northern California. So given that these events are highly impactful and low predictable, the scientific community has made a tremendous effort in trying to understand their dynamics in order to predict them. So there has been many work, and I'm just listing a very few here. For example, on subseasonal time scale, this work by Ten et al. Found that a specific teleconnection pattern across the Pacific is responsible for some of the heat wave events occurring in the US, which allow potential prediction up to 20 days in advance. On seasonal time scale, for example, the Pacific North American pattern, which is a weather pattern occurs in the Northern Pacific, has been shown to modulate drought and extreme heat over the US. However, these two patterns are highly unpredictable on interannual timescales. So on interannual timescale, there has been many work looking at sea surface temperature anomalies as a potential modulator of interannual variability of these extreme events. And even beyond on multi-decadal timescales, a pattern, ocean pattern, sea surface temperature pattern in the North Atlantic, namely the Atlantic multi-decadal oscillator, has been shown to modulate drought conditions and heat waves occurring in northern Mexico and the western United States. More recent, our work here, my colleagues and I, we found that on interannual timescales, variations in the intensity of the East Asian monsoon do modulate heat waves occurrence in the Great Plains of the US. For example, what we found is that active monsoon summers can induce this Rossby wave teleconnection pattern across the Pacific, which leads to enhanced blocking and high pressure dome over the central US, which promotes persistent weather and extreme heat waves. And this work that I'm going to present here today is a further advancement of what we found in 2019, but now linking in more local SST anomalies regarding the Atlantic 1 pool. So for this work, we are using several data sets. We use daily and monthly mean air temperature and atmospheric circulation pattern from the ECNWS 20th century reanalysis. We also have some the most recent ERA5 version of the reanalysis, but what I'm presenting you regarding heat wave is using the longer term 20th century reanalysis. We also use daily and monthly mean precipitation data from GPCP project, as well as the sea surface temperature comes from the Hadley Center version 2 at a 1 degree resolution. We also use extreme temperature and precipitation indices from the Hadley Center, as well as daily maximum temperature from several station data that dates back to the early 20th century for several stations in the Great Plains of the US. We also rely on fully coupled models. We look into the 20th and 21st century projections of CESN large ensemble simulation, as well as CIMIC-5 and CIMIC-6 models. And also we perform several atmospheric general circulation experiments to assess the role of SST on heat waves. But before I have to present to you how I define these extreme events. We define heat waves based on our 2018 paper by performing a cluster analysis. Before we perform a cluster analysis, first we compute a temperature anomaly. This is 2-meter air temperature anomalies, and only retain those temperature anomalies exceeding the 95th percentile threshold based on observations. Then we perform a spatial smoother to isolate any what they call hot grid points, which are uncharacteristic of large-scale heat waves. We remove those. Then we only retain anomalies that persist for at least a minimum of 3 days. Then we obtain these spatial temporal anomalies of extreme temperature and perform a cluster analysis, where we cluster these temperature anomalies into their most common patterns. And these are the most common patterns for North American heat waves coming from observation in the left panel and the CESM large ensemble simulation in the right panel. You see that the model does reproduce at least does make a good estimate of the large-scale spatial patterns of the most dominant heat wave occurrence in North America. But these are too many heat waves, so we only concentrate on a very few spatial cases based on the underlying population that have been affected by each of these heat wave patterns. So we computed the number of the population affected by each of them and only look at the top 4 most affected. So, and this is our work in 2018. We show that for the 4 dominant patterns, there's a very broad and highly diverse response to climate change, to anthropogenic forcing. So we computed what's known as probability of necessary causation based on ratio of probability of present climate and future climate against the pre-industrial epoch. And we're able to compute what's known as the time of emergence of the anthropogenic climate change signal on top of natural variability and assign a specific temporal scale of when we might expect climate change to be the dominant driver of heat wave occurrence. And we found a very distinct spatial pattern of when this may happen. So for example, in the Western US, for this heat wave cluster, anthropogenic climate change will be the dominant driver of heat waves compared to natural variability as soon as the next decade. Whereas in the Great Plains, these 2 clusters here, it appears that large natural variability or large model error are blurring the anthropogenic forcing. So we may expect, because of large natural variability or model errors, most of the heat waves occurrence, at least in the models, in the future projection over this region, is driven by internal dynamics. So we want to understand what's actually driving these internal dynamics in order to predict them, right? So we look at the large ensemble future projections of CESM. This is one model, the top panel. And then this is CMIT 5 and CMIT 6 future projections, multi-model. And we look at the ensemble spread, basically the uncertainty in future projections of surface temperature. And what we found is a very coherent pattern between the large ensemble and the CMIT 5 and 6, showing that over the Great Plain, the ensemble spread, which is an indication of internal dynamics and model error, dominates. Whereas in the 2 extremes of the country, like in the eastern US and western US, there's very certainty that, or at least as measured by the ensemble spread, of future projection of surface temperature. And the reason why I'm showing you here these 2 different models is that the large ensemble is just one model with multiple ensembles. We have 30 ensemble members for this model. So any difference, or as measured by the ensemble spread, is purely internal dynamics, internal variability, or natural variability in the model. Whereas the spread here in CMIT 5 and CMIT 6 is not only internal dynamics, but also different model physics or model errors. But you can see that the 2 patterns are very similar, and most of the amplitude of the spread can be explained by internal dynamics alone. So we have to understand what is driving internally dynamics in order to better understand heat waves, for example, and extreme temperatures in this region. So why is this region special? Well, the Great Plains, they're home to probably one of the largest regions here where soil moisture and surface air temperature communicates through what is known as the land-atmosphere feedback. And this is in a schematic here shown. For example, dry soil moisture increases sensible heating and decreases latent heating, which tends to increase near surface air temperature, which then tends to feed back and further dry the soil. And this is only at play in specific regions here, as shown in this map by the work of Coster et al., where in the Great Plain, there is a delicate balance between soil moisture, long-wave radiation, sensible heat flux, and latent heat flux. So only these regions here is where this strong coupling and feedback are at play. And this is because, for example, in other regions, let's pick a random region in the northeastern United States, there is abundant soil moisture to modulate latent heating, but there is not enough long-wave heating and not enough solar radiation. So the radiation is a limiting factor here. Whereas in the western United States, This is the other stream. There is enough long wave heating, but not enough soil moisture. So soil moisture is a limiting factor. So there is a sweet spot, namely in the Great Plain of the US, where soil moisture can actually modulate surface temperature. So what is driving soil moisture in the Great Plains? It has been shown that the Great Plain is home of something called the Great Plain low-level jet. And this low-level jet, usually very low in the atmosphere, peaks in boreal spring and summer, is responsible for up to 1/3 of the moisture transport and precipitation in the Great Plains. And this is what I'm showing you here. This is climatology of circulation at 925 hectopascal. And I'm highlighting here in color the meridional wind. So you see the jet here entering mostly off the Texas coast. And a recent study showed that the origin of the moisture transported by the Great Plain low-level jet originate mostly in the Caribbean Sea and Gulf of Mexico. So it seems that SST anomalies in this region may actually modulate the Great Plain low-level jet, which eventually may modulate heat waves occurrence in this region. So we perform a composite analysis. Again, this is the climatology circulation at 925, and this is the anomaly circulation at 925 during Great Plain heat waves. We took the cluster analysis we performed. We only kept the Great Plain cluster of heat waves and performed a composite analysis. And this is what is shown. During heat waves, there is a negative anomaly in the circulation at the low-level jet core. As you can see here, this is a cross-section in this region showing in contour. This is the climatology. Positive means northward, and the anomaly during heat waves minus climatology during June, July, August. And you see that during heat waves, the low-level jet is reduced. We use the future projections in order to further understand this relationship between low-level jet and heat waves. Again, this is shown here by climatology, just for reference. This is the same picture as before. But now below, what I'm showing you is the future projection of the Great Plain low-level jet in CIMIC 5 models. And you see that in CIMIC 5 models, the low-level jet is projected to increase in amplitude and slightly shift northward. But still, there's associated moisture transport with these anomalies. So in the future climate, the low-level jet is projected to increase, namely because of difference in trends in this surface temperature between land and ocean. So increased land-ocean temperature contrast increases the low-level jet. And we can validate this further by looking at each individual model as a function of a scatter plot for different regions in the Great Plains. What I'm showing you here in the x-axis is changes in the Great Plain low-level jet amplitude, 21st century projections minus 20th century. In the y-axis, what I'm showing you here is changes in heat wave days over this region, over the Great Plain, for the northern Great Plain and the southern Great Plain. And you see a very nice negative correlation between models that show increased Great Plain low-level jet shows the least increase in heat wave occurrence. And by the way, I should point out that all models show increased low-level jet, and all models show increased number of heat wave days in the future climate. So this negative correlation is just a relationship between that rate of increase in the low-level jet versus the rate of increase in the number of heat wave days. So based on this analysis, it becomes important to assess natural factors that may be influencing the low-level jet variability and its relationship with the heat wave occurrence in this region. And one natural factors very close to home here that came to mind is what's known as the Atlantic 1 pool. The Atlantic 1 pool is this western hemisphere high sea surface temperature that encompass most of the Caribbean, Gulf of Mexico, western tropical Atlantic, and here eastern tropical Pacific. But for the purpose of this work, we only concentrate on the Atlantic side of the one pool. This one has been shown to modulate Caribbean Sea convection and Great Plains low-level jet as well. And also it modulates North American rain through modulation of the moisture transport associated with low-level circulation changes. And the Atlantic 1 pool is predominantly intrinsic to the Atlantic Ocean, its variability. And the variability is dominated by both interannual and multidecadal component. The multidecadal component is tightly linked to the Atlantic multidecadal oscillator, AMO, as was found by David Enfield, 2001. So here in this work, we want to build upon what is known already when it comes to Atlantic 1 pool modulation of atmospheric circulation associated with Great Plains rainfall and drought condition when it comes to extreme weather events, mostly heat waves. So to do that, we define what is an Atlantic 1 pool. An Atlantic 1 pool is defined based on Wan et al. As an area index. So we computed the area encompassed or enclosed by the 28.6 isotherm. And we have this area. Now, this area index, we do that for every June, July, August, or JJA. And this area index is normalized by its climatology. So here, what I'm presenting here is a time series of JJA from 1950 to 2019 of the area index. And it's shown here as a percentage because it's normalized by the climatology and multiplied by 100. So to show that, for example, large 1 pools are much larger relatively to climatology than small 1 pools. So there is a very large skewness in this area index. And here, what I'm showing you here in this panel is the composite of those large 1 pool years, basically the upper tercile of this time series, and the composite of the small 1 pool, and the difference between large 1 pool and small 1 pool, showing basically most of the linear response occurs in the interior of the ocean. So basically, what it does is, since this is an area index, the large 1 pool tends to extend eastward into the interior of the tropical Atlantic. So this is where most of the anomalies lies. So now, for this analysis, we perform a composite analysis. Since this is a highly nonlinear index, regression is not a good approach because we may be missing a lot of nonlinearities here with a regression analysis. So from now on, I'm going to show you composite analysis of large 1 pool years minus a small 1 pool years and the respective anomalies. So this is the atmospheric response to large 1 pool minus a small 1 pool. And you see that this is all for June, July, August. This is mid-level 500 millibars of circulation anomalies and precipitation in color. You see a strong anticyclone located in the eastern half of the United States, and reduced precipitation in the southern portion of the country, as well as the Great Plains, especially the southern Great Plains. We further look at moisture transport and its divergence, which is shown here in this vector. This is the transport and the divergence of that vector, which explains very well that this deficit in rainfall is driven by the horizontal moisture transport anomalies, as well as the divergence of that. And you see here dry over moisture transport divergence associated with probably weaker Great Plains low-level jet, which I'm going to show you later. And here, this is a composite of a precipitation index, a standard precipitation index. I show dryness in this region as well as in the eastern United States. And we perform a cross-section analysis similar as before over the main entrance of the low-level jet, which is here along the Texas coast. And in climatology, you see this is the climatology low-level jet, and these are the anomalies. But these now are anomalies with respect to moisture transport. Basically meridional moisture transport. So you see that during large 1 pool minus small 1 pool, basically, during large 1 pool, there is a reduction in the northward moisture transport associated with the large one pool. And it's mostly driven by changes in the circulation, so changes in the wind rather than changes in moisture content, where in fact during large one pool year you have enhanced, by here this positive color in green, you have enhanced moisture but reduced transport because of the reduction in the low level jet. Here we look more extremes. Again, perform a composite during large one pool minus a small one pool for several extreme indices. Heat wave days, and you see increased heat wave days in the Great Plains during large one pool. We also look at maximum temperature, which is the highest temperature for a given month. Again, increase over the Great Plains and the eastern United States. We look at diurnal temperature range, which is a good estimate of clear sky. It's also enhanced during large one pool, as well as the extreme temperature range and the number of days that exceeds the 90 percentile threshold, which is highly consistent with the heat wave days. We also look at the extreme drought days. So these are drought days, persistent drought days, composite large one pool minus a small one pool, and you see significant drought over basically the southern plains as well as the eastern United States. We also look at changes in the distribution of these are from observed temperature from station data at different airports, which dates back, several of them dates back 100 years. So we look at Chicago International Airport, St. Louis, as well as Oklahoma City, and you see that for those summers where the one pool was large, there is a warm shift in the PDF of surface temperature, which is significant compared to the small one pool years. And these are show changes in the mean, which are on the order of 1.5 degrees Celsius for the one pool years, large one pool years relative to the small one pool years. I mean, it becomes more notorious as you go south, as you get into the southern plains. So now with that, this is all from observation. So we want to really isolate any external factor that may be blurring or interfering with this composite analysis. So for that, we perform an atmospheric general circulation experiment where we use the atmospheric and land component of CESM2, and we prescribe large one pool SST anomalies and small one pool SST anomalies. And before we perform any experiments, I would like to show that this model is able to replicate the stream threshold that I use here for definition of what a heat wave is. So what I'm showing you here is the observed 95 percentile threshold of daily mean surface temperature. And this is from the model. So the model does show a fairly consistent distribution of the very stream threshold here, which is the 95 percentile. So this is very important, not only depicting the mean, but also the stream of the PDF if we want to look into AGCM experiments. So as I mentioned, I prescribe large one pool SST anomalies as shown here. And then I also prescribe a small one pool and SST anomalies. And this is just for show here. I'm showing just the asymmetry between what is a large one pool and a small one pool. It's mostly warm asymmetry. So you have a skewness there. As we show, not only there is a skewness in the index, in the area index, but there is also a skewness in the amplitude index as well. So we run this experiment at about 1 degree horizontal resolution. And this is, by the way, coupled to the land component of the model, because as I mentioned before, surface temperature and soil moisture are strongly connected in the Great Plains. And we've run each case for 300 years. Why 300 years? Because we need to extract meaningful statistics to compute what a heat wave is, based on our very strict definition of a heat wave. So this is the response, the model response. Again, presented here as large one pool minus a small one pool experiments. So you see, it doesn't come as a surprise that there is enhanced what we did was we performed these AGCM experiments by prescribing large one-pool SST anomalies and small one-pool SST anomalies. And what we show is, as expected, enhanced rainfall over the Caribbean associated with a very robust northward shift of the ITCC. And you see here this is outgoing low wave radiation anomalies. You see a reduction in the outgoing low wave radiation, which is a response of increased convection. But we also see enhanced outgoing low wave radiation in the continental US, which is probably associated with reduced cloud cover and enhanced outgoing low wave radiation. So this is the low level response during warm and small one-pool years, and it's a very characteristic cyclone to the northeast of the maximum SST anomalies. Basically, it's collocated over the Gulf of Mexico, and you see a very marked reduction in the climatological southerly associates with the Great Plains low-level jet. So during large one-pool, there's a reduction in the Great Plains low-level jet. So the model results basically confirms what we see from observations and what had been reported before. And here we look at the cross-section associated with the Great Plains low-level jet for the observed, again, large one-pool minus a small one-pool, and the simulation using the AGCM experiments. Climatology is shown by the black contour and the anomalies in color. So both the model and observations show a very consistent story that large one-pool reduces the southerlies and reduces the moisture transport along this latitude line. And we were able to compute the number of heat wave days in this simulation and did a composite, and you see that for most of the US, there is an enhanced number of heat wave days for the simulation of large one-pool compared to those with a small one-pool. So in conclusion, this work identified interannual variability of the one-pool as a modulator of heat wave occurrence over the Great Plains. And when the one-pool is large, there is a enhanced atmospheric convection in the Caribbean Sea, which produces this low-level cyclonic anomaly over the Gulf of Mexico, which further weakens the Great Plains low-level jet, creating more drought conditions over the Great Plains. And due to the fact that Great Plains is a region of strong atmospheric land and soil moisture feedback, this actually feeds back into modulation of surface air temperature, not only in the mean, but also in the streams as well. So in addition, since future projections of heat waves are more uncertain in the Great Plains, as was shown in our 2018 paper, it's very important to identify these natural factors, for example, the large one-pool, as I presented here, or the remote monsoon teleconnection patterns as a potential predictors of interannual variability of these extreme heat waves. So for future work, something that I have omitted here, a recent paper from one of my colleagues, Dong-Min Kim, in 2020 found that it's not only the Atlantic one-pool, but the interhemispheric SST anomalies between what occurs in the Atlantic Ocean versus what occurs in the tropical Pacific that really modulates US rainfall. However, this study is based on late summer, August, September months, but I want to test this hypothesis of interbasing SSTs as a potential modulator of midsummer heat waves. As well, for future work, I'm very intrigued on what occurred this past summer regarding heat waves. We have two very extreme cases, basically a few weeks apart, one in the southwestern US and one in the northwestern US, which I mentioned before. And I want to investigate the co-occurrence of these extreme events, why and what drove them to occur during the same year and why they were so extreme. And you can see here in our cluster analysis, two of the clusters really represent these two extreme events. Like the southwestern cluster is well collocated with what we saw for this extreme case this year, as well as the northwestern cluster.
is well collocated with well representing the temperature anomalies of the very extreme record-breaking extreme heat waves that occur in the Pacific Northwest. And so I want to use this as a phenomenological motivation for further assessing heat waves occurrence, the spatiotemporal changes, as well as their future projections. And thank you, that's all I have.